periodic trends. Periodic trends. The basic idea here is, how do we understand the properties of elements on a periodic table? There's a couple major trends we can worry about. The first one is the least sexy. We have Z effective. Is the effective nuclear charge. The whole idea is that as we move from left to right, top to bottom, we're going to have the Z, which is our atomic number of protons, is going to be increasing no matter what we do. However, the number of electrons will also be increasing, usually at a proportional rate. But there's a thing that the electrons, as we move from left to right, top to bottom, the electrons on the outermost layer feel the nucleus at a different effect. Because if we're looking at, I say, like a nucleus here, electrons on this layer would feel it greater than electrons here. I know, yeah, I have way too many electrons for the number of protons, but we'll just put like a bunch of pluses in here. So we have a nucleus. These guys are going to feel the nucleus a lot more because they're closer. These guys are going to feel it a little bit less because they're farther away. It's like two magnets. You bring magnet at a distance. And these electrons provide what we call shielding. Electron shielding effect. That it's going to block the magnetic layer. Just like in radiation, we put up lead shields to block the radiation from leaking through. We're putting up electron shields to block the nuclear attraction. However, the electrons do not shield perfectly. And so what we have is a trend that electrons between layers shield well. Electrons within layers shield poorly. And so we have a simple trend that the Z effective, which is the effective nuclear charge, the effective attraction that an electron in the outermost layer feels, the effective increases greatly from left to right, and increases weakly top to bottom. It's going to increase going top to bottom, but not by very much. If you looked at a trend on a graph of Z effective versus Z, it's like da 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 da. Like each time it's going a little bit higher, then it dropped down, not quite to the same height. Because if we did from here, we're seeing a net increase between each row, but it's a large increase within a row. But that is our first trend, our Z effective. Second trend has to do with size. Now the size will depends on orbitals, and Z effective. So all things considered, as you bring out orbitals, each orbital is going to be slightly farther from the nucleus, slightly farther from row 1 to rho 2 to rho 3. It's getting farther and farther and farther from the nucleus. However, you're also increasing the Z effective, so it's pulling it back in. So depending on how the Z effective goes, we could see an increase or decrease. So typically, as you move from left to right, size decreases. Size decreases because it's all same orbital, but Z effective goes up, increase. So they're within the same orbital, but Z effective increases. So that means, just looking at that, lithium is way bigger than fluorine or what's a neon, just because of where they are. Top to bottom, size increases. Increases because new orbital, but Z effective only has a slight increase. And so if we go down, hydrogen, lithium, neon, potassium, rubidium, cesium, francium, we're getting bigger and bigger and bigger because we're going from rho 1 to rho 2 to rho 3 to rho 4. So we're putting new orbitals around there because the size all depends on electrons, the electron cloud. So anything that shrinks the electron cloud makes it smaller. Everything that grows the electron cloud gets it bigger. And so looking at that, we can say that a cation is always smaller than a neutral, and an anion is always bigger than a neutral. So if I compared hydrogen and proton and hydride, so this is allowed. H can gain an electron or lose an electron. H plus is smaller than H, but H minus is bigger than H because the cation and the anion, we just added an electron to the cloud, so it grows bigger. We removed an electron from the cloud, so it grows smaller. And this allows us to actually determine an isoelectronic series. So what this isoelectronic series means is we have the same electron count, but different number of protons. So if I just said, we'll say from sodium, using the electron configuration of neon. Neon has 10 electrons total. So if we compared sodium, magnesium, aluminum, and fluorine, and oxygen, and nitrogen, they all have the same electron count, but we get most positive is the smallest, most negative is the biggest, because we're just adding more electrons, and so the protons have a poorer time trying to hold on. Now we have really two more trends. Sorry, lights keep on going off. Our first trend is our ionization energy, which is the energy it takes to remove an electron. Energy, E cost to remove an electron. This is going to depends on size and Z effective. Because essentially, how well does the nucleus hold the electron? How well does the nucleus hold the electron? How far do we have to move it? Because when we ionize, we're talking about we have these infinite layers of orbitals surrounding here. Some of them aren't filled, some of them are. We could excite the electron to one energy layer, but to ionize, we have to move it out to infinity. Of course, infinity, each energy layer is smaller and smaller and smaller and smaller distance. So you reach a limit of what the energy is. You reach a limit of how the energy difference. So we have to make this fully escape. So how far does it have to go before that happens? Well, Z effective is how well does that nucleus hold on to that electron. Size is then how many energy layers does it go. Electron on the first layer has to go farther than electron on layer number 4. Even if the Z effective is slightly bigger than layer 1, that has less places to go. We're already closer to the desired destination. So right here, moving left to right on the periodic table, the ionization energy will increase. It increases. That's because, remember, Z effective increases and size decreases. So we have both things are negatives working against each other. Working with each other. So ionization energy would increase. But moving from top to bottom, ionization energy decreases. Largely because size increases. There's one other thing to worry about with ionization energy. Ionization energy is that removing a second or third electron always increases energy. Why? If you think about it, well, when you remove an electron, it becomes positive. What happens to the size? What happens to the size when it becomes positive? The size gets smaller. What happens to the Z effective? The Z effective gets slightly bigger. So when you remove an electron, size gets smaller, Z effective gets bigger. Both of those things would cause ionization energy to increase. But one big thing to note is there is a large increase when removing the first electron from a row. Electron from a new row, filled row. So, for example, we could remove one sodium electron, sodium to sodium plus 1. But we're going to have trouble going from sodium plus 1 to sodium 2 plus because we'd have to start on the neon row. Sodium plus 1 is the same electron configuration of neon. So to remove a second electron would be to start on a newly emptied, a fully filled row. So that's going to have some trouble. Now the last trend is our electron affinity. Electron affinity. Now electron affinity is the energy gain by giving an electron. Giving an electron. This is essentially the opposite of ionization energy. Instead of removing an electron, we're putting an electron in. Remember how we talked about thermochemistry and how we talked about light? If it takes energy to move it out, it must give energy to put it back. We're putting energy in. So this also depends on size and Z effective. But there's also factors of electron repulsion that we have to take into account. That throws a lot of things off. Typically, from left to right, electron affinity generally increases, but there are notable exceptions. For example, when we go from, if you're talking about like sodium to magnesium, you might see going from sodium to magnesium, you might see a bucking of the trend because one electron pairs it up. And so you would have to pair two electrons, which are repulsive. Then we see a big jump when we add magnesium, because magnesium goes to aluminum, and that is an unfilled p orbital. And then aluminum, silicon, then phosphorus. Phosphorus will buck the trend again because this is a half-filled orbital. All the electrons are unpaired. To put an electron into here, you would have to pair up an electron. So to put this new electron in means I have to pair up electrons, so this counterbalances. So phosphorus drops to 0. And then it's once again sulfur. It increases again, sulfur, chlorine. And then we see no gain on argon. Argon is 0 because argon has a completely filled row that doesn't want a new electron. Top to bottom, we also see a bucking of the trend. Electron affinity slightly increases. And this has to do with that even though Z effective increases slightly, but size increases. But the size increase means less repulsion, less electron repulsion. So even though you would expect electron affinity to go down, the fact that these two electrons, this new electron we're putting in there has more room to roam, if you say. It's moving around the electron cloud. It's less likely to run into its other electrons that are currently there. And so we see, it actually less of an effect. Now, one more thing we can talk about is, this isn't really a trend, but just looking at crystallization energy, the lattice energy, because if you put all these things together, if you try to calculate what is the energy to go from, say, sodium solid and chlorine gas to sodium chloride solid, what energy does it take to make this? If you use all the things you learned about the vaporization, you have to turn this into a gas. You have to ionize this. You have to split this apart. You have to then give this an electron. If you put this all together and then crystallize as a solid, you're like, this right here is a very big, is exothermic, is going to produce a lot of energy to do this. But if you try to calculate the energy from all the little steps, you would get short of the energy by a lot. That's because lattice energy, which is the energy to go from sodium plus gas and chlorine minus gas to sodium chloride solid, is a huge uptake. And the lattice energy can be calculated. It's essentially, there's a constant involved that we don't need to really worry about, but it's typically the positive charge times the negative charge divided by the distance. The positive charge, the negative charge divided by the distance. The absolute value, by the way. So +1, -1. Typically speaking, what that means is larger positives, larger negatives means more lattice energy because you have more attraction. Sodium chloride would be a 1 and 1. If I said magnesium chloride, I would have a 1 and 2 because I have a 2+ charge on the magnesium. If I said magnesium sulfide, I would have a 2 and 2 because I'd have a 2+ and a 2-. So typically speaking, the more charged the molecule, the greater the lattice energy, the greater the attraction. However, the size, the bigger the size, the farther the atoms are apart, and so the less attraction they can have. Because the nucleus has to get close. So the bigger the atom, the smaller they are. So if I compared sodium chloride versus lithium chloride, because lithium is smaller than sodium, would have a greater lattice energy. Because it's smaller than sodium. If I said, instead of lithium, if I said potassium chloride, it would have a lower lattice energy because potassium is bigger than sodium. But typically, this is the #1 defining factor on when we talk about size.